Hello everyone, today we are doing Knapsack problem. We are solving this using AI search algorithms by Lisan Algaib. So the problem statement. The 0-1 Knapsack problem is a classic NP-hard optimization problem. So this is a special case from the fractional knapsack problem where the goal is to select a subset of items such that the total value is maximized without exceeding a given capacity. The task is to determine whether there exists a subset of items whose total weight does not exceed W while maintaining the maximum total value. So with the knapsack having maximum weight W and each item I has a value Vi and weight Wi. So we compare performances of uninformed and informed algorithms. Uninformed being BFS, DFS, IDFS, and in informed we are looking into best first search. State space representation. Number of states. N equals to I comma W comma value, where I is from 1 to n plus 1, when W is a set of all the weights and value is the value of that particular weighted element. Action. At each state, there are two possible actions we can take. One is to exclude the item and one is to include that item. Start state. We start at I equal to 1 at maximum weight W and not taking any items, that being 0. And our goal state is to find the state at which the weight does not exist maximum weight W, but the price or the capacity we get is the maximum. So let's look at the algorithms we are going to use for this. BFS, breadth first search, explores level by level, complete but slow, very high space and time. DFS, explores branch by branch, very low memory usage, but can get stuck in loops and is not exactly optimal always. IDFS, iterative deepening DFS. This combines the best of BFS and DFS. It is complete and optimal like BFS, but with the low memory usage of DFS. And best first search. We use a priority queue to expand the state with the highest value so far. Let's look into it. BFS. We explore the search tree level by level using a queue. At each step, we exclude current item I plus 1 W comma value, or we include if it fits our criteria. When I equal to n plus 1, we record the best value. Going on to time complexity. In the worst case, the time complexity is O of 2 power n, and the same applies for the space complexity. So BFS does not use any heuristics, so it explores all states systematically. This is nothing but similar to brute force. The strength of it is it does guarantee a optimal solution, which is a complete solution, but the weakness is the memory blows up and there is an exponential runtime. DFS explores all possible subsets recursively. At each item, branch into exclude or include choices, same as BFS. Once it hits a dead end or a complete solution, it backtracks to the last decision point and tries the next available path. We track the best value when reaching I equal to n plus 1. So in worst case, time complexity is the same, O of 2 power n, but we have an advantage in space complexity. Only recursive stack of depth n is being stored, so only O of n. Performance. As same as BFS, we do not have any heuristics here. We explore all states systematically by going as deep as possible down one path before backtracking. We have excellent memory efficiency and the same weakness as exponential runtime. So IDFS, iterative deepening DFS. Here we combine both BFS and DFS and do something in between. Depth limited DFS is called repeatedly for increasing depth from I to n. At each limit, allow recursion only up to that depth at a given. Best value is updated when reaching the leaf states. Time complexity. Here the time complexity is O of 2 power d, where d is the depth. But if you look at the worst case, the optimal state might be at the bottom, making it O of 2 power n. Space complexity. Same as DFS, recursive depth O of n. It does not have any heuristic. It systematically explores by performing a series of depth-limited searches, effectively searching level by level. It combines the best of both worlds of BFS and DFS and gets the complete and optimal solution. Again, the problem is it has repeated computation and exponential runtime. So let's move on to our algorithm, which does contain heuristics. Best first search approach. We use a priority queue to expand the state with the highest value so far. At each step, we expand I, W and V into exclude or include children. Continue until all items are processed. Ensures promising state high value are excluded earlier. So whatever are the more promising states are they going to be explored before the ones which may look not much favorable. So this is kind of similar to a greedy approach. If you look at the time complexity, it uses a priority queue to always expand the state with the highest value so far. So in the worst case, it will be n into 2 power n. Space complexity, priority queue stores up to O of 2 power n states. So O of 2 power n it is. A key advantage of best first search is its ability to find a solution more quickly than uninformed search methods by using a heuristic function to prioritize more promising nodes. Weakness. The effectiveness of the search is highly dependent on the quality of the heuristic function. A well-designed heuristic can lead to a quick solution, but one which is not well designed will have way worse than even brute force. Let's look at some performance metrics. What we use here are time complexity, space complexity, and the nature. Here in this table we can see BFS has time complexity O of 2 power n, space complexity O of n, and if you look at the nature, it explores the full state space level wise. DFS brute force subset search, IDFS same as DFS with repeated passes, best first search, heuristic driven bound exploration. So from this we can conclude that brute force BFS is also very infeasible for huge search space. Same with DFS and IDFS, but best first search is the fastest of all three and can have many optimal solutions. Thank you.